Good afternoon, everyone. Welcome back. Thank you for joining us. I'm Steve.
And I'm Scott.
Together, we are Backyard Musings, the Science and Technology channel.
Yeah, and we are talking about some science, almost science, like in some cases it could be considered science fiction. But this is definitely not fiction. This is something that could happen and probably has happened, right?
Yeah, it's really cool. Solar scientists report that they have identified an important source of powerful gamma rays released during the sun's most extreme eruptions. According to research published in Nature Astronomy on January 7, 2026, a team from NJIT's Center for Solar-Terrestrial Research has identified a previously unrecognized group of high-energy particles in the sun's upper atmosphere. These particles appear to be responsible for mysterious radiation signatures that scientists have observed during major solar flares for many years. Would you like to know more?
Hey, so how'd you like to walk up to somebody and say, "Hey, where do you work?" "Oh, I work at the NJIT Center for Solar-Terrestrial Research." "Oh, really? Cool. What are your hours?"
What are your hours?
Jeez. All right. The researchers traced the signals to a small, concentrated area of the solar corona during an intense, whatever this means, X8.2 class flare on September 10th, 2017. In that region, they detected enormous amounts of particles reaching energies of several million electron volts, or MEVs, far exceeding the energy levels typically associated with solar flares and traveling at speeds close to that of light. So solar flares, I mean, these are the deals that can knock out our electric grid, right?
Yeah.
Communications, electric grid, not good.
Yeah, GPS. Yeah, it affects ships navigating on the ocean. Yeah. Scientists think these particles produce gamma rays through a process known as Bremsstrahlung. Sounds German to me.
Okay.
In this process, lightweight charged particles such as electrons release high-energy radiation when they collide with matter in the sun's atmosphere.
The research team says this findings help resolve long-standing questions about how solar flares generate extreme radiation. It may also lead to better models of solar behavior, which could ultimately improve predictions of space weather.
Quote, "We knew solar flares produced a unique gamma ray signal, but that data alone couldn't reveal its source or how it was generated," said Gregory Fleischman, NJIT-CSTR research professor of physics and lead author of the study. Continuing his quote, "Without that crucial information, we couldn't fully understand the particles responsible or evaluate any potential impact on our space weather environment. By combining gamma ray and microwave observations from a solar flare, we were finally able to solve this puzzle."
To pinpoint the source of the radiation, the NJIT researchers brought together observations of the 2017 flare from two complementary instruments. These included NASA's Fermi Gamma Ray Space Telescope and NJIT's expanded Owens Valley Solar Array. Oh, I know where that is. Oh, that's up there that's up there by Big Pine. And an advanced radio telescope system located in California. I had no idea that was. I thought that was all Caltech and NASA, but maybe they're collaboration. Cool.
The Fermi telescope recorded detailed measurements of high-energy gamma rays emitted during the flare. At the same time, EOVSA provided microwave images that revealed where energetic particles were moving within the solar corona.
When the team analyzed the two data sets together, they identified a specific area in the solar atmosphere known as Region of Interest 3, or ROI3. This region stood out alongside two previously examined areas, ROI1 and ROI2, obviously, because it showed overlapping microwave and gamma ray signals, pointing to the presence of an unusual population of highly energized particles.
This convergence pointed to a unique population of particles energized to MEV levels. Quote, "Unlike the typical electrons accelerated in solar flares, which usually decrease in number as their energy increases, this newly discovered population is unusual because most of these particles have very high energies on the order of millions of electron volts. with relatively few lower energy electrons present, said Fleischman.
Using advanced modeling, the team linked the energy distribution of these particles directly to the observed gamma ray spectrum, pointing to the Bremsstrahlung emission, high energy light usually produced when electrons collide with solar plasma, as the elusive source of the gamma ray signals.
Fleischman also says their observations with the ROI-3, located near regions of significant magnetic field decay and intense particle acceleration, support long-standing theories about how solar flares accelerate particles to extreme energies and sustain them.
Quote, we see clear evidence that solar flares can efficiently accelerate charged particles to very high energies by releasing stored magnetic energy. These accelerated particles then evolve into the MV peaked population we discovered, says Fleischman.
So a thought popped in my head. I wonder how this information might be used for the tokamak fusion reactors. They're creating plasma in there and trying to sustain it. And they're using AI to predict the flares so they can control the flares. I wonder if this could help. I'm going to give him a call.
Okay. Yeah. Let us know how that goes.
For now, Fleischman says key questions remain about these extreme particle populations. Future observational insights could soon come from NJIT's expanded Owens Valley Solar Array, currently being upgraded to EOVSA-15. This project, led by NJIT-CSTR Professor of Physics and EOVSA Director Bin Chen, a co-author on the study, is funded by the National Science Foundation and will enhance the array with 15 new antennas and advanced ultra-wideband feeds.
Wow. You know this place that I'm talking about, right?
I think, yeah.
Just as you pass Big Pine, there's probably, and some of those little dish antenna are pretty small, and some of them are on tracks where they can move them, they can move them along the ground rather than having to adjust the antenna location. So, okay, so I'm reading the last one, right?
Yep.
Quote, one big unknown is whether these particles are electrons or positrons, Fleischman said. Again, going on with the quote, measuring the polarization of microwave emissions from similar events could provide a definitive way to tell them apart. We expect to gain this capability soon with the EOVSA-15 upgrade. So, very cool.
Something interesting, the android from Star Trek, Data, he had a positronic relay. Positrons.
Yeah, and what about, we got electrons, we got positrons. What about Megatron? You know who Megatron is?
Yeah, I do. Megatron, a bad dude. Bad dude.
Yeah, Transformer guy, right?
Yeah, bad dude.
Yeah. So, I mean, I've seen him on some YouTube clips down there at Universal Studios. So, he's kind of rude.
If you become a minion, he'll backstab you.
A minion?
Bad dude.
He doesn't like minions?
Well, no, I mean, if a henchman, if you become one of his henchmen, he doesn't care. He'll backstab you. He'll use you for all you're worth. Bad dude.
Oh, sounds like a Democrat. Okay. All right.
That's a good one.
All right. Well,
thanks, folks.
Talk to everybody later. Thanks.
We'll see you tomorrow.
See ya.